Hello and welcome to Topics in Statics. I'm Dr. Setz. This will be a series of videos to help introduce you to some of the general principles necessary to be successful in Engineering Mechanics Statics course. Let's get started. Mechanics is a branch of physics that deals with things that are moving. In general, we break it up according to the types of objects that are moving. We talk about rigid body mechanics, deformable body mechanics, fluid mechanics. This class will primarily deal with rigid body mechanics. Then we also discuss how the bodies are moving. And so we break it up into two big areas, statics and dynamics, which depend on how the object is accelerating. In statics, it's not accelerating, and in dynamics, it is accelerating. We use a number of models. The most important ones we use, these are just idealizations to help us simplify problems. The first is a particle. We'll start off talking about particles. A particle is an object that has mass, but it has no size. It's a mathematical point. Then we'll extend our idea of an object to be a rigid body. And that's one that when I apply forces to it, it doesn't change shape. And the other big idea we use is concentrated forces. We assume that forces act at a single point. In reality, when a force is applied to an object, that force is applied over some area. But for the most part, we're going to ignore that. Obviously, since mechanics is a branch of physics, we need to know a good bit about physics. And here's the types of things we're going to need to know about. You should have covered all this in a physics course at some point. Newton's laws of motion, there's 3 of them. The big one is going to be the second law. The sum of the forces is equal to the mass times the acceleration. We also use a little bit of Newton's law of gravitation, weight, spring force. You'll notice that all 3 of these are magnitudes. These are not showing you how to calculate the vector force. These are just showing you how to calculate the magnitude of the force. Here for spring force, you'll notice spring force, this S, this is the displacement of the object. We use slightly different letters than you use in physics, but it's the same idea. There's nothing new on this page. These are just the types of things that you need to be familiar with. If you're not familiar, go back and look at your physics book and remind yourself of some of these things. All sciences rely on types of measurements, and the types of things we measure are what are called dimensions. And in mechanics, there's only 4 dimensions we need to worry about: length, time, mass, and force. The only reason I bring this up is because once I decide what units I want to use, that determines what system of units. So the way a system of units works is I choose a base unit for the 4 quantities on the previous slide. In this course, we're going to use 2 different types of units. We're going to use SI units, which are System International, that's metric system. And then we'll use US customary units. And there's a slight difference between the two because there's only 4 units that we have to define. But in reality, I only define 3 of them, and then the 4th is determined by Newton's second law. So in the SI system, they just create units for length, time, and mass. The meter, the second, and the kilogram, those are defined. Somebody picked what those were going to be. But then once I've picked those 3, I use Newton's second law to solve for what force is, and that determines what my standard unit of force is, the Newton. A Newton is a kilogram meter per second squared. In the US customary system, the 3 that are defined are different. Again, they choose length and time, but instead of mass, they choose force. And so in US customary units, we define feet and second and pounds. And then the unit of mass is derived from Newton's second law. You've probably never heard of the unit of mass in U.S. customary units. It's called a slug. And 1 slug is a pound second squared per foot. Why does all that matter? It matters because when you start working problems, particularly when you're dealing with weight, how you figure out these quantities is from the definition of weight, from Newton's second law. Weight is mass times the acceleration due to gravity. And in the SI system, typically problems will give you a mass and you have to calculate the weight. So you use that first equation there. And the acceleration due to gravity is 9.81 meters per second squared. That's probably the way you did it in physics. In US customary units, it's much more typical that they'll describe an object and they'll give you its weight. They'll tell you it's 12 pounds. Well, now if you need to calculate the mass, you have to rearrange that equation. And so the mass is the weight divided by the acceleration due to gravity. And in US customary units, the acceleration due to gravity is 32.2 feet per second squared. Conversions between systems, hopefully you're familiar with all the types of conversions. Unit prefixes, same thing. We still use kilos and milli and mega and all those things. The one thing you need to notice is 1,000 pounds in US customary is sometimes abbreviated KIP, kip. So 1 kip is a kilopound. Dimensional homogeneity. What that means is whenever you write an equation in physics or engineering, the equation applies not only to the numbers you're putting in there, but it also applies to the units. So if the left-hand side of the equation is in feet, the right-hand side of the equation also has to be in feet. So you might have an equation, for example, x is equal to x0 plus v0t plus 1/2 at squared. So this is a standard constant acceleration equation. This left-hand side is measured in the length. It's a feet or meters or something. So each of these quantities over here on the right has to be in. And there's 3 quantities over here. There's 3 things I'm going to add together. And the only things I can add together are things that have the same units. So x0 refers to some position. Again, it's in feet, meters, whatever. v0t, velocity times time. Well, this is going to be velocity is length over time times the time. Gives me a length. Good thing, that works. And then 1/2 at squared. The 1/2 is just a number here. A is the acceleration, which is in length over time squared. And then I multiply by time squared. And so again, I end up with a length. So dimensionally, that equation is homogeneous. This is a really good way to check your algebra. If you're doing some complicated problem and there's a whole lot of algebra involved, don't plug the numbers in and try and figure it out. Just figure out what your dimensions are and make sure that they're correct at the end of all your algebraic manipulations. Significant digits. This is a huge bugbear for most students. The idea of a significant digit is you're trying to express to somebody else how well you've measured that number, whether it's the length of the table or speed of the car on the interstate. So, for example, if a number is reported as a 27, just 27, that indicates it's known to be somewhere between 26.5 and 27.5. Right? If instead I said something was 34.2, I've measured it down to that 0.2, so I know it somewhere between 34.15 and 34.25. So what about numbers like 1100? That's real ambiguous. It's hard to say. There's rules for how many significant digits that has, but the point is it's very ambiguous. The easiest solution to to numbers like that is to write them in scientific notation. So I could write it as 1.1 times 10 to the third. That would indicate that I know that number somewhere between 1,050 and 1,150. Or I could write it as 1.10 times 10 to the third, which would indicate that I know that number to be somewhere between 1099 and 1101. So significant digits are much easier to deal with if you write things in scientific notation. And there's a lot of rules for how you do algebra with significant digits and all those things. I'm not going to go into all that. They're important. The big trick is don't round numbers until the very end. That if you round too soon, if you round a number to 3 significant digits and then you do further calculations, you've lost some accuracy. In general, I would keep at least 4 significant digits through all intermediate calculations, and then at the end I would round to 3. And for this class, we're not going to talk about significant digits a whole lot. We're not going to deal with them, but all your answers are expected to be given in 3 significant digits. So keep more in any prior calculations. And that's it for the introduction. Next time we're going to start talking about vectors. And until then, good luck.